In 2008, a routine rescue on the surface of a vast freshwater lake in the Netherlands initiated a prolonged forensic investigation. The Markermeer is a broad, shallow body of water characterized by heavy silt and almost no visibility below the surface. When a private yacht ran into trouble, the KNRM rescue service became involved. During that rescue operation, an anchor became the accidental instrument that exposed something buried in the mud. The anchor caught in the soft sediment and lodged against something unyielding. When the obstruction was brought to the surface, the corroded geometry was unmistakably aircraft-related. It was a component from the landing gear drive system of a heavy bomber. This single point of contact located a forgotten crash site, but it did not yet settle the aircraft's identity. The wreckage belonged to a Royal Air Force short Stirling Mark III. The Stirling was a massive 4-engine heavy aircraft, utilized extensively for night operations during the Second World War. The stakes of this investigation were entirely forensic. The state-funded mandate was not designed to recover an aircraft for a museum display. The objective was the systematic extraction of human remains from an incredibly hostile underwater environment to provide closure to the families of the missing. The engineering teams faced a strict boundary. They had to execute a complete site clearance to ensure no crew members were left behind, while operating under conditions where traditional visual archaeology was completely impossible. The immediate aftermath of the 2008 discovery highlighted the dangers of premature identification. With no intact wreck available to read, investigators had to build the aircraft's identity from recovered fragments. They recovered a small group of objects and fragments from the immediate area around the exposed landing gear component. One badly degraded airframe fragment appeared to carry an identifying number, and that reading pushed the investigation toward a specific missing squadron aircraft. For years, the site was treated as the wreck of Stirling BK716. This initial verdict bypassed the rigid evidence discipline required in modern aviation archaeology. For more than a decade, the public narrative, the family campaign, and some memorial interpretation rested on that uncertain reading. The problem with circumstantial evidence in a high-impact debris field is that fragments can be misleading. Personal items, detached panels, or generic equipment do not constitute a definitive identity lock. A forensic identity requires a stronger chain of evidence linking recovered components to the aircraft's wartime record. Without that kind of primary mechanical evidence, the identity of the Markermeer wreck remained technically unproven. The long gap meant that a compelling historical narrative had formed before the decisive physical proof was in hand. Leaving the aircraft in the mud was not a viable long-term strategy. The delay had allowed engineers to measure the scale of the problem. Not an intact airframe resting on the bottom, but shattered metal, possible ammunition or unexploded ordnance, and biological material swallowed by dense sediment. The anchor snag proved an aircraft was there, but it gave no reliable data on the spread, condition, or identity of the debris. The site, therefore, required an industrial intervention capable of turning assumption into physical verification. In 1943, a Royal Air Force short Stirling Mark III bomber, operating at night on its return from Berlin, was shot down near the Markermeer. It did not glide into a controlled ditching. It struck the water at high speed, and the kinetic transfer shattered the heavy bomber airframe on impact. That lost mechanic defined the later forensic problem, while the 4 Bristol Hercules radial engines remained among the densest and most durable pieces in the debris field. The sheer mass of the short Stirling, one of the heaviest bombers of its era, produced a vast field of individual components. Engines, landing gear, cockpit instruments, ammunition, wing sections, and fuselage fragments ended up dispersed through the mud, leaving investigators with a broad and irregular wreck field beneath the water rather than a single coherent aircraft. Following the violent surface impact, the secondary phase of the site formation began. The Markermeer does not feature a hard rock or packed sand floor. The lakebed is composed of highly viscous, semi-liquid silt and heavy mud. This environment created an immediate and permanent entombment mechanism. The shattered components of the Stirling, particularly the solid steel engine blocks, heavy main landing gear assemblies, and defensive machine guns, possessed significant negative buoyancy. Driven by their own dead weight, these items punched directly through the soft top layer of the lakebed. They sank deep into the sediment until they reached a point of physical equilibrium. Once the heavy debris settled, the natural lake currents rapidly swept lighter silt over the impact craters, smoothing out the floor. The resulting low oxygen burial created a difficult forensic trade-off. It helped shield some material from direct exposure and disturbance, but it did not stop corrosion or biological degradation altogether. Enough physical evidence survived for later recovery, yet that evidence became extremely difficult to locate, separate, and interpret. However, this same preservation mechanism completely erased the visual footprint of the crash site. Because the wreckage was entirely swallowed by the sediment, the site became a zero-visibility environment. Divers operating on the lakebed in later years could not see their own hands, let alone manually map a complex, highly fragmented debris field. There was no intact fuselage to follow and no visible wingspan to anchor a survey. For crew recovery, traditional underwater photography and visual grid surveys were therefore unusable. Engineers had to treat the site not as a sunken ship, but as a submerged mining operation. A wreck field roughly 75 meters by 75 meters forced a complete reevaluation of standard recovery engineering. Sonar, radar, and metal detection surveys of the Markermeer lakebed established the true physical boundary of the forensic challenge. The data revealed a massive, irregular distribution of metal anomalies, proving that the heavy bomber had not remained centralized. To clear the site and systematically retrieve the missing crew, engineers needed to access and process a football field scale area of underwater mud. The 75 by 75 meter boundary set the scale of the required industrial intervention. Planners first tested the dry site option, a cofferdam or sheet pile enclosure that could isolate the wreck field from the surrounding water and expose the lakebed for controlled excavation. The attraction was clear: better visibility, easier access, and a cleaner chain of custody for biological evidence retrieval. But the Markermeer was open water, and enclosing a 75 by 75 meter recovery area would have required a major civil engineering project before the forensic work could begin. Safety concerns, possible ammunition, cost, schedule, and the risk of an unstable enclosure damaging the evidence all weighed against the method. The National Recovery Program therefore rejected the dry cofferdam proposal, eliminating visual dry land processing as the primary route. The decision prioritized the safety of the working crews and the preservation of the site over the convenience of a dry excavation. However, it created a massive new procedural hurdle for the investigation team. Planners had to formulate an industrial sequence to systematically clear the buried material without removing the water. The method and schedule now had to bend around those safety constraints. The team had to secure the biological evidence and the defining mechanical components while operating entirely submerged. If engineers could not safely push the water away, they would have to pull the fragmented wreckage directly through it. With dry excavation unavailable, spatial control had to come from machines rather than sight. The extraction phase required deeply buried material to be removed from resistant sediment while preserving a usable relationship between each fragment and its original position. To execute this wet recovery, the engineering contractor deployed a specialized extraction sequence utilizing heavy marine equipment. They anchored a massive floating pontoon directly over the designated underwater sector. Mounted on this primary platform was a heavy industrial excavator equipped with a specialized digging bucket. However, the operation of this machine was not guided by the eyes of an operator looking into the water. Instead, the entire dredging sequence was governed entirely by satellite positioning. A high-precision GPS system was integrated into the excavator operation. This system allowed the team to record the bucket's position and depth to about 5 centimeters. This blind spatial control meant the machine could remove lakebed sediment in systematic layers rather than digging random holes. By tying recovered material back to the mapped extraction area, the team preserved a workable archaeological grid, even while operating completely submerged. Once the heavy bucket cleared the water, the payload consisted of dense, viscous mud containing a chaotic mixture of heavy clay, shattered aluminum, ammunition, and potential human remains. The first pass was a safety screen, using a coarse 30-centimeter sieve because the team did not yet know whether the aircraft had dropped its bomb load before the crash. Only after that initial hazard check did the material move to the nearby processing pontoon for finer separation. High-volume water jets washed the heavy mud across an industrial sieve equipped with a rigid metal mesh screen. The openings on this screen measured exactly 8 millimeters, or roughly 5/16 of an inch. This specific geometric dimension acted as a strict physical filter for the entire operation. The highly viscous mud and fine silt were structurally broken down by the water jets and forced through the mesh, returning safely to the lake. Simultaneously, any solid material larger than 8 millimeters, whether a heavy engine mount or a tiny biological fragment, was trapped securely on the upper deck. This continuous stream of trapped material moved across a mechanized conveyor system, requiring immediate forensic and hazardous material triage. To process this chaotic output, a specialized 4-person team continuously monitored the mechanical sieve. This operational protocol was strictly enforced to manage severe localized risks hidden inside the mud. On the conveyor, an ammunition specialist separated degraded machine gun rounds and other small hazardous remnants that had passed the coarse bomb load screen. A radiation expert continuously scanned the debris stream with specialized sensors to detect and secure fragmented flight instruments. Many aircraft instruments of the period used radioactive paint for low-light visibility, so shattered cockpit dials required careful monitoring before manual inspection could proceed. Behind the hazard control layer, an archaeologist and a human remained specialist cataloged the viable evidence. Every fragment retained from the 8 millimeter screen was immediately logged against the digital coordinate of its original underwater extraction point. This continuous loop of mathematical dredging and mechanical sorting successfully bypassed the zero visibility constraints of the environment. The biological remains were isolated from the heavy clay and placed under a strict chain of custody. The massive volume of mechanically sorted debris now had to yield the single piece of evidence that could definitively identify the bomber. The machinery from the lakebed now had to settle the aircraft's origin. The decisive standard was an identifying number on a primary aircraft component that could be checked against wartime records. During the first week of the underwater recovery, the extraction equipment brought up a Bristol Hercules engine block. That discovery became the most durable structural evidence on the site. In the end, all 4 engines were recovered, along with landing gear, cockpit instruments, fuel tank material, wing sections, and fuselage fragments. The thick metal of an engine casing offered a better chance of preserving an identifying number than painted skin or lightweight placards torn apart by impact and decades of degradation. Relying exclusively on these recovered blocks shifted the forensic process from historical interpretation to strict mathematical verification. Every heavy military aircraft engine is stamped with a unique alphanumeric identifier at the time of manufacture. These identifiers are permanently recorded in the squadron maintenance logs and directly tied to the specific airframe they power. Maintenance crews document every engine swap or repair, creating a precise paper trail that links the specific serial number to the exact airframe configuration on the night of the loss. The proof now depended on whether those marks had survived. Investigators then had to expose and read the identifying marks without damaging them. Decades in the lake had covered metal surfaces with mud, corrosion products, and hardened deposits. Cleaning had to be controlled and conservative because the value of the component rested on the survival of the number itself. Once the identifying point was exposed, investigators cross-referenced the number against the surviving wartime records. The recovered engine evidence did not support Stirling BK710. It pointed instead to short Stirling BK716. The conclusion was reinforced by additional recovered structure, including an aircraft panel that still carried the BK716 marking on the inside. The physical machinery and the surviving marked panel together dismantled the long-standing assumption. This identification pivot corrected the historical accounting of the aircraft and the personnel lost with it. The previous designation had offered an answer, but not the right one. The correction demonstrated the danger of relying on damaged or circumstantial evidence in an aviation archaeology context. By enforcing stricter evidence discipline and relying on primary mechanical identification, the investigation established the aircraft's identity on a durable physical basis. Only then could the operation move to its human objective. Exactly 7 individuals constituted the absolute metric for operational success. Following the resolution of the aircraft identity, the investigation narrowed entirely to the biological evidence. The mechanical sifting process executed in 2020 recovered fragmentary remains and separated them from the heavy lakebed clay. However, the physical mesh did not differentiate between human bone, shattered cockpit plastic, aviation insulation, or naturally occurring organic lake debris. Everything larger than the dimensional limit arrived for examination in a heavily commingled state. The specialized team did not recover intact anatomical structures. Instead, they inherited a chaotic stream of material that had to be systematically separated and meticulously categorized under strict conditions. All matter suspected of being biological was transferred from the floating processing barge to the secure facilities of the Royal Netherlands Army Recovery and Identification Unit. Inside the military laboratory, osteologists began the slow, procedural process of visual differentiation. They had to manually isolate human osteological fragments from the surrounding environmental and mechanical material. Once this strict biological baseline was established, the investigators faced a rigid mathematical constraint. With highly fragmented remains, traditional identification methods could not be assumed to produce named individual matches. Prolonged immersion in an aquatic environment can severely degrade organic material over 7 decades. That condition narrowed what the laboratory could prove. Public reporting later stated that it was impossible to assign the remains to individual crew members. Genetic identification was therefore not presented as a successful individual matching process, and the biological evidence had to be handled as collective fragmentary remains connected to the verified aircraft and crew manifest. The historical military ledger still mattered, but it had to be handled carefully. The verified aircraft identity established which crew was on board BK716 when it was lost. The biological evidence confirmed that human remains had been recovered from that wreck field. Instead of producing 7 separate personal identifications, the recovery allowed the crew to be commemorated and buried together, with all 7 names restored to the correct aircraft and the correct crash site. This final recovery phase concluded the state-funded mandate. The massive industrial effort, which involved mobilizing heavy dredging equipment, engineering mechanical separation chains, and managing hazard triage, was dedicated to recovering the crew and correcting the record. Once the wreckage and remains had been processed, the underwater archaeological grid was formally closed, and the specialized extraction pontoons were demobilized from the open water. The technical limits of a zero-visibility burial environment had been systematically mapped, mechanically bypassed, and forensically addressed. The operation replaced a 12-year historical error with documented certainty about the aircraft's identity and closed the case on a verified forensic record.